All right, guys, welcome to another conscious endeavor. Here we are talking about the nature of the self, reality, consciousness, and all that good stuff. We got a good episode for you guys today. Specific Mr. Special Guest here. We're going to be talking about a little bit about physics. We'll be discussing a number of things on how that all operates. My buddy Tae here is physics enthusiast, big on the nature of consciousness, a bit of a mindfulness practice person himself. So very cool, very interesting topic and conversation we'll have today. So I'm kind of want to open this up with just again, we're talking about a little bit more about physics today, talking a little bit about the science, getting into some of those things. Really, again, talking about the interface here between biology and, physical principles. Again, biology's taking advantage in a way of these physical attributes, of matter. Right, which is, again, really interesting. Cells, develop membranes. They're able to isolate certain minerals, for example, sodium, potassium, right, within neurons, and they can exchange those to create function. So a very interesting, something that gets derived from that, right, how this function starts to occur and how our interplay with reality sits. Yeah.
I think the most one of the most interesting things about physics is it's like the application of the unknown. And what I mean by that is it's not entirely intuitive. Like, for instance, we understand how gravity works and, but like things such as electricity, magnetism, relativity,
right?
How, the curvature of space-time and things like that are not necessarily intuitive to us. And a lot of the times they've been more or less been, developed through trial and error till we had that breakout miracle year of, I think it was 1905 when Albert Einstein published his theory of special relativity.
And he met with, what is it, Heisenberg and all these other people in that one.
Oh, the Solvay conference.
Right. Yeah. I mean, very interesting too. And it's interesting that you bring up like the fact that it's not intuitive to us. Because a lot of times what we try to do is like we're always anthropomorphizing a lot of these concepts. I mean, even like, for example, like electron flow.
Right.
We say that electron flow moves from like positive to negative when we talk about and think about electrical systems, right? But the electrons are actually flowing in the opposite direction of that. Right. So it's kind of interesting. Again, it's like we put these human concepts a lot of times on what we believe matter to be and what we think it should act and order like. But I mean, again, we're kind of taking our own concepts and trying to, again, put it into a mold which suits our own thinking already. But tenets of science are always, about constantly changing because, again, scientific revolution leads to these kind of changes in thought and revolutionizes the way we think about certain concepts.
I like how you said that because it is a constantly developing field based on empirical studies. And it's very interesting now too because you have an entire different branch of physics that's focused on the theoretical aspects of it, and that's constantly changing. Like, for instance, you have, stuff like string theory, multiverse theory, and how everything fits into it. So if I may just explain just real quick, there's something called the standard model of physics, and that's basically what we have to describe the things around us, as in we have the electrical force, gravity, and the strong weak nuclear force and all the interactions between them. And so we do have like this blueprint, basically, that we're able to test out, mathematically verify. And using that, we try to basically mold our, like, the basis of what we can assume to be correct, at least, for, everything from the range of the universe to the age of the universe and everything in between, how things came about. And there are a lot of laws, theories, and even mathematical values that are very, very specific. For instance, the speed of light, the expansion of the universe, and like even like the mass of an electron.
Right.
You know, you have a number that's like 10 to the negative 23.
Right. Super
very,
small.
very small.
Yeah.
And it doesn't work if, you know, if it's a 1 over or 1 below.
Right.
And
well, it's interesting.
it's interesting.
We see it like a kind of a perfect balance of forces a lot of times.
Right.
You know what I mean? The exact charges and the exact mass. I mean, it's what made these things inherently come together was the fact that they were balanced forces.
Right.
You know, they talk about the Big Bang, for example, and how like if it happened like, you know, a second faster or probably like a millisecond, you know what I mean? But like a little bit more energy or a little bit less energy, like, you know, galaxies would have flew apart. They would have never formed. You know, if it was too slow, the gravity would have fell in on itself. You know, so it's really interesting how you have this kind of perfect balance that originates and really science trying to pull apart. I mean, naturally us working in these reductionist kind of paradigms where it's like we have to try to pull this apart and understand this as interacting pieces, and then how do those pieces then influence each other, you know? But I mean,
right. And you know, it used to be just the atom, but now we know that, you know, you can break atoms down further into like 6 different types of quarks, and then you can break those further down into, I don't know, quantum fluctuations, which are ridiculously complicated and probabilistic. And it's actually a miracle almost to be able to like have these types of this groundwork almost that's so advanced in mathematics and, you know, it's spatial geometries and stuff. And now we have technology being able to complement that and perhaps even simulate it, you know. And I think one of the more interesting things about science as well is that it also, in a sense, gives you there's some deep philosophical truths that I think you could derive out of certain laws of nature. For instance, you know, like one of Newton's laws, like, you know, for every action, there's an equal and opposite reaction. And, you know, things will always be in motion until, you know, something else, you know, stops it, like, you know, and things like that. And so I feel like with one of the focal points that physics is trying to do is at least bring about what we know as the base layer for foundation for at least what everything from matter to energy, heat, like thermodynamics and things like that. And we use that to basically build, you know, the next layers of the branches of science, like chemistry, biology, and things like that. And, you know, in a way, you know, I actually think that the universe has a very nice sense of humor.
Yeah.
You know,
I mean, it's interesting too, because I mean, as we kind of build again this like the scaffolding, I guess, you know, of like how we understand matter, how we pull apart matter, you know, our conscious minds are sitting atop this kind of ever-existing phenomena, or as far as like maybe what the human mind, you know, if we only live less than 100 years, you know, like what sort of, you know, understanding can we grasp about that? But, you know, again, as generations and generations go on with written language, you know, we were able to kind of, you know, build upon these structures that we inherently, you know, create, and then we teach. It's interesting too, because every time I read a book like, you know, physics or psychology or whatever, it's like, you know, a lot of times you're reading someone's life work.
Right.
You know what I mean? And then you're reading it at the age of like a teenager or whatever, you know? And now you're like, okay, well, this is now the base layer, and that base layer continues to evolve.
Right. And I find that so interesting because, I mean, they say that, you know, the idea of the atom came from the Greeks where, you know, atomos or atom, you know, it was some dude who was thinking about things and...
Everything's made up of indivisible pieces, right?
Indivisible pieces.
I think atom
fundamental
meant
building
like
blocks.
Unbreakable.
Right. And you have kind of like ever since, you know, Newton, you know, he really made his Principalia, you know, with his theory of motion, gravity, and everything. He basically launched everything into the stratosphere with even like the layer of of calculus, which basically is, you know, one of the ways that we have to kind of understand, and it's not intuitive. It's very hard. You know, there are a lot of concepts that you know one would have to, you know, go through, but ultimately, those concepts have basically evolved, and they help us to like fill in the pieces for what's missing and what we don't know. Like for instance, there was a guy named so when we talk about like electricity and magnetism, there's like three different laws. It's called Maxwell's equations,
Right.
and it's based on the ideas of three different physicists and mathematicians. They were like Gauss, Faraday, and basically they were trying to explain like exactly what is the nature of electricity and magnetism and stuff like that. And it's a very, very complicated field when you break it down into when you're like trying to solve like electrical fields and magnetic fields and stuff like that. But like the concept of opposing currents,
Right.
and the forces of those strengths for electrical currents and magnetic currents, and
Right, which are it's just a
Right.
coupled force.
you're right,
Right,
like
so
an electrical field
Right.
gives rise to a magnetic
Right.
and
Yeah, and I think
magnetic
that's an
field.
important concept definitely just to address too, is because that electromagnetism being one force, everything gets induced via the other, right? So if there's a magnetic field present, and let's say a piece of metal moves through that magnetic field, it's going to induce a current
Right.
in that piece of metal because it's entering a magnetic field. And therefore also, because there's a current in that metal, right, that current will also induce its own magnetic field. So electromagnetism is just one force and it's glued together. So, again, if you send copper through or electricity through a wire, right, why they have that insulation is because they're creating a small magnetic field around it, right? So this is the really interesting property. And also thinking about, even if we think about the brain, because we know that the brain is to some degree sending these electrical signals, and there is what we call myelination in the brain, which is like these fatty substances which sit on the top of neurons, or on the top really of the axon of the neuron, which sends signals. So it's interesting that the biology kind of actually took that into account, in terms of how biology is inherently intelligent and how it utilizes these
Right.
forces. So it becomes very interesting. And again, just to, think about that too, because when, again, if the body has this electrical potential in terms of the nervous system, there's also a magnetic counterpart
Right.
to that.
Right.
You know? I mean, bringing that in is always really interesting. And a lot of times too is some of these concepts, I feel like in science, where certain people don't talk to each other, in terms of you saying the physicist versus, the chemist then coming up with an idea, and then the biologist and then the psychologist, these people are not really regularly having conversation. And you need to, again, like, newer fields like biochemistry and biophysics, where they're trying to now bring in these ideas of what are these principles.
I believe that's the key.
Yeah.
Yeah.
You know.
Because when you have these disciplines starting to cross over each other and overlap each other, and that's when you basically have, I feel like, a whole new exploration and potential.
Right. Paradigm shift.
Right.
Yeah.
And you kind of need that in a way. I understand, everything with specialization, it's a very, very, it's a necessary part, But at the same time, like even robotics, for instance, it's like you're using, everything from muscle memory and how like the neurons of, your hands are
Right.
put together, and you're trying to simulate that into like an actual metallic thing, that you can like touch and,
Are you talking about a robot?
yeah,
Like a
yeah,
robotic
like
hand?
robotic hands,
Right.
and things
yeah.
like that.
I mean, a lot of it too is like, it's very interesting because there's so much mechanics built into just even the operation of this weird like tool that you have.
Right.
You know what I mean?
Yeah.
And yeah, when we try to recreate it, we realize how complicated those systems really are.
Right.
You know.
And one of the cool things about this, at least this century, or this the beginning of the
Where we
2000s and where we exist right now,
Yeah.
is there's a lot of like, I think space mining and like exploration of space is we something we could potentially see in our lifetime.
Yeah.
like at least the initial beginning stages of it, and it could have such a massive consequence to how things turn out to be. And there is something called the Kardashian Scale, and it basically talks about if there were like other civilizations out there, for instance, like a type 1 civilization on the Kardashian scale would be a species that is capable of harnessing the entire planet, the entire energy of the planet. And a type 2 would be, a civilization that can harness the energy of their neighboring star.
Neighboring star?
Yeah.
Wow.
Yeah.
And
in their own solar system. And most stars are actually binary, which is also
you mean their
sun?
sun?
Yeah.
Right. Not a okay.
And type 3 would, you could scale that out to a galaxy, for instance. And, of course, we have, who's that guy? He said, well, if there are civilizations out there, well, where are they?
Right.
Fermis Paradox, I think. Yeah. Fermis Paradox.
Yeah.
And so there's like on the opposite spectrum of that, you have something like the rare earth theory that that life is very, very, very hard to come across, and it's a very, very rare thing.
Yeah.
And it's, as far as we know, we are the only species that exists. But if you open up yourself to different the possibility of what's out there,
it's interesting too, because like in terms of it takes billions of years allegedly for like complex life forms to arise. So we have this, like, you have to have stability in that solar system for a fair amount of time in order for these complex systems to kind of develop. And
those conditions also seem to be like very rare, for instance.
Right. I mean, we have like, telescopes looking for other planets and things like that. The interesting thing too is that, a lot of times we had certain parameters for like what made life possible to exist.
Yeah.
For example, like it was like, oh, well, we need sunlight, we need water, and we need like, I think there was like a third thing. But it's like interesting because now we think that those are the parameters for life to exist. But now sunlight was one of them. We thought a planet needed that. But then we found under the ocean that where there was hydrothermal vents, there was a whole species of like crabs that originated from there that adapted to that environment, and they had zero access to sunlight. They weren't there was nothing in their food web that was photosynthesizing. For example, in the food web near the surface of the ocean, we have plankton, right? And then like the small fish and like even whales would eat plankton. And then, they would like feed another ecosystem. The small fish get eaten by the bigger fish. This whole kind of system, but which still originates and has the necessity of the sun. But in these, subaquatic, areas, there's no need for it. So now all of a sudden that becomes not a parameter. We don't actually need the sun because this hydrothermal energy was giving the energy for these organisms to exist and kind of create their own ecosystem minus what we thought was necessary for life. So I'm thinking once we start to explore these planets, we might have such different parameters of what life is, or what we might potentially find. I feel like we have no idea what we might find.
Like, I'm glad you mentioned those species that are deep down in the ocean, because even if you like scale time back like millions and millions of years ago, we didn't have that much oxygen on the planet, and yet all this oxygen, or a majority of it, was created through like some form of algae. They would take sunlight and they would release oxygen into the atmosphere, and over billions and billions of years or so, we have what we have today. And
they call that like the chemical soup, right? Having that the appropriate amount of mix of molecules in order for life to arise. Right. Allegedly.
Right.
But it's really interesting too, because like, where does the first mover come from, right? Because again, an organism is something that like creates a membrane and walls itself off from the environment, aggregates certain minerals. It might like swim over and get some, calcium and some magnesium and find these specific minerals, and then, incurs a function within itself. and then also grows and evolves. I mean, like for example, like fungi, some of
That is
the
interesting.
earliest, organisms on this planet. They found a fossilized mushroom that's like 2 billion years old, not too long ago, and it like literally had the same shape of a mushroom it has today. So it's like thinking about the adaptability of these organisms, and for example, those mycelium networks are these underground mushrooms, right, that are growing, or underground fungi systems. They're able to very quickly adapt. They can find, for example, like they can be as long as a football field under the ground,
Right.
and one end of it might find a particular thing that it can't digest. So it'll literally start to develop an enzyme to eat that thing, right? And then all of a sudden, all the way on the other side of it, that organism, like really they're all connected, right? But now the fungi on the other side of, 100 yards away also develops the enzyme, because they're constantly sharing that information,
Right.
right? And how adaptable they are, and how they're able to, again, in terms of the physics here, just take different minerals, find a potential for them, find a use for them. It's interesting how like that, in a way, is intelligence.
Right. Yeah. No, I understand what you're saying. And a lot of the things that of physics that like we talk about, or at least we, read in textbooks and stuff, it's not like nature. It's like, oh yeah, let me, do this and do that. It's like built into, I guess, like the fabric of reality, I would say. And we have that as the foundational base layer. And, it's interesting that you were talking about first mover. I mean, if we go back to the origins, we have like, Big Bang and things like that. And even like matter, antimatter, and, all those, like the 1% matter that was supposedly left over after the initial,
So yeah, in the Big Bang, there was a lot of creation of antimatter as well as matter. Those things destroyed each other.
Exactly.
And the leftover matter had a little bit more left and was able to arise.
Yeah. And it's very, very cool how just being able, like we have the first verified photo of the black hole in our own galaxy, Sagittarius A star, which came out around April or May of last year, 2022. And it's just such a interesting phenomena that, when you trace things back, many distance away, and you kind of have, at least for me, you can't feel anything else but awe in a way, and just the way how things turned out, and how much left there is to explore, and how much we don't know. And
it's interesting too, as the black hole, like we think that's a destructive force. We think about, the black hole, it's gonna like eat everything and destroy everything, but literally, like as the theory goes nowadays, like there's a supermassive black hole at the center of every galaxy, which is incurring this ability for stars to revolve around the galaxy and create this movement. And it's interesting because out of that kind of so-called destructive process, that this aggregation comes in, right, where now these star systems and gas clouds potentially that were maybe completely uniform at one point, if a black hole comes close to it, starts spinning it and pulls it, and now all of a sudden it's in this gravitational lock, and then as those matter moves, they might condense and form their own star, and then stars revolve around, like our sun, for example, revolves around a larger star, right? And not a lot of people know that, right? Because it's like this just system of wheels upon wheels of like revolution and all that momentum that's really going into matter on this planet, which is interesting too. I mean, this idea of spin that's within everything. I mean, atoms are spinning, molecules spin. Enzymes in your body spin very very fast. You know what I mean? And now like this incursion of energy, as we would measure it, is kind of embodied in all of that.
And I think that's such a cool concept, because when you get down to it and learn about these things, like I said before, a lot of stuff in physics and chemistry and biology are not really that intuitive to us. But like the discoveries and post discoveries they're mind blowing in some way. And this is why I love like this field so much, because
kind of just every day you're just like Okay.
Yeah,
Mind
yeah.
blown each. You
Yeah.
know? That's awesome.
You mentioned about black holes, and there is a very, very interesting phenomenon in space that's called the booties void.
Okay.
It's one of the blackest regions in the universe out there. We really can't explain it. Like, I'm not even sure if I can do a good job of explaining it. But basically, if you could imagine, you have, you ever seen that picture of, like stars out there in the universe and stuff like that?
Right. Like
and then there's
Hubble
just, and then there's just a layer in that map that's just completely black.
So it's just like there's nothing there.
Right. And so people, scientists have tried to, peer deeper into that area. They call that area the booties void. And it's a very, very interesting phenomenon. They actually think that there's a theory out there that it might be the remnants of a Type 3 civilization.
Because it's taking the sunlight for energy.
Like you have Dyson Spheres around the sun or something.
Right.
And
so just to clarify that, Dyson Spheres, for those of you who don't know, are essentially giant, and how we would kind of describe it as solar panels that completely encase a star, right? So that you're literally just taking the energy out of that star and utilizing it. And probably sending it wirelessly and who knows what, you know what I mean? Like connect to the Bluetooth.
Yeah. And it's a space that we really don't know too much about. However, and I think it also plays on the imagination.
Right.
It's like what could be out there, and
it's the beauty of science too. I mean, in a way, it's like we do remain objective and practical, but at the end of the day, you do have to suscept yourself to some of this just awe-inspiring things, and like to understand how, because science is very, very good at understanding how things work and what happens when we apply certain laws. For example, everyone's really familiar with that textbook example. It's like, well, if you shoot a ball at this many degrees at this speed and it weighs this much and gravity is this, you can predict exactly where it's going to fall. The
trajectory, exactly.
Right? You know what I mean? So pinpoint all of that. So when under the application of specific laws, we're able to kind of figure out a lot of these things. But what gets interesting too is that it seems with physics that there's different domains of physics. So for example, on this scale we're talking about, planets, spheres, black holes, we have classical mechanics, right? Classical physics, right? But then again, I know everyone at home is probably like, are they going to talk about quantum physics yet? So that's really, a whole other domain,
right?
Because again, these forces really apply and have different application depending on the scale.
Honestly, when it comes to quantum physics, it's such a hard thing to like actually have an application about.
Right.
Because it's such an abstract probability cloud that you have with Schrodinger's equation, and it's really, really it plays on the mind, because basically, you have these concepts like superposition, two things can be at the same time. They even one of the Nobel Prize of Physics this year came from proving Bell's inequality about quantum mechanics, and basically that means that what it means is that they proved that the information that apparently like two photons have, like up spin, down spin, or whatever, and no matter the distance, how far apart it is from each other, like when one thing happens to one quantum state, it will instantly apply to the other.
Right, and this is what most people know as quantum entanglement. When two pieces of matter are entangled, if they were previously connected, when one gets affected, it affects the other.
Yes.
Instantaneously, faster than light.
And that's the implication of that, because we use that as the constant to basically derive time and, how fast things can go and, things like that. So it's just a field that, like, it really takes someone who's dedicated, thousands and thousands of hours to really understand this stuff, and at the same time we somehow use, in a way, like quantum mechanics, like to make silicon chips, and to manipulate like how small you can make like the silicon, like an atom layer thick or something, and set them up and arrange them in a way that, like, you increase computation power and things like that.
Wow, you could make a computer chip an atom layer thick. That's insane. Or like I mean, the interesting thing too, again, is that we traditionally use electricity as just the flow, allegedly, again, of these electrons.
Right.
Right. So like, essentially, matter being these the nucleuses of atoms, and the electron then traveling across, kind of just following it like a conduit, like just really I guess essentially thinking about it like a really, really thin wire. But again, just the application of a lot of those things and where they pan out, also because it's like our minds, in terms of especially the speed and the scale at which quantum fluctuations happen. I mean, before you even snap your finger, a trillion probably quantum interactions are occurring.
Right.
You know what I mean? So taking advantage of that scale, I mean, they talk about quantum computers. There's a couple, neuroscientists now trying to talk about quantum states of things in neurons. Yes. So neurons, again, obviously being
Roger
built.
Penrose.
Yeah, Penrose, Stuart Hameroff, all these couple people, but talking about how these fluctuating states of atoms, right? Again, being susceptible to the laws of physics.
And the implications of that is that, or at least for Penrose, is somehow quantum mechanics is intimately tied to the biology of neurons,
Yeah, what consciousness is to some extent, quantum explanations of that.
And it's mind-blowing in a way. It's like, in a way, it's like physics and it's like physics and chemistry, came together, they created the universe, and then biology comes along. It's like, oh wow, this is so cool. And then and then it looks back and it's biology learning about physics and chemistry, which is what created.
Yeah, I know there's some joke about how like a scientist studying like atoms is like a group of atoms studying itself.
Right.
You know what I mean? It's just really interesting. But yeah, biology inherently being this organized framework of like, again, how I kind of rationalize it is that we have biology kind of taking advantage of these inherent properties in matter. Right. You know what I mean? Like, for example, like potassium and sodium, they have certain ionic charges, right? Those minerals or those, molecules or elements, whatever the hell we want to call them, right, have their own kind of, properties. And then somehow, whether it be, if we can even call it intelligence, our body knows, right, which one to use for what function, or to some degree. I mean, because there's always the parallel between this kind of like, well, it was that biology was intelligent, or there's like some sort of intelligent design, but then there's also this emergent property that like through these properties of matter, those things arose. But then it's also hard to say, well, how does like what was like the first membrane?
Right.
Like, how did did it accidentally just form a membrane and then function incurred because of the difference in concentrations of things?
Right. Yeah.
And whether that, then also thinking to the macroscopic as us as complex organisms, right? How are we now, I mean, we're maintaining an equilibrium within the environment, but then again, we're incurring function. And then you can think about purpose in this grand scheme of like cosmic / quantum, interaction. It's like, what are humans doing? What is this, specific
That's where
phenomenon?
I find neuroscience to be particularly attractive, because, I mean, I understand that, everything outside the domains of the hard science, aren't as, straightforward with,
harder things to apply too. I mean, it's psychology.
Like, there's no mathematical concept to a personality,
right?
And I feel like it's such an interesting phenomenon where you have, that we even have a field that, we're basically looking into the brain at least, and we. Everything down to the axiom, to a neuron, and to the neural network, and how it spreads out, and potentials, and how you were mentioning, even the potassium and the ion channels, and even their interactions, and you're just breaking down everything into the anatomy of the brain in a way, and how that reflects upon human behavior and things like that, and it's such an interesting thing. I know we were talking about physics, but that's eventually what you get, like things like neuroscience, and who knows what else is going to come next. If we do really master and like understand like the human brain and like how computation and memory and how all these things, and it is a little bit of a scary thought for me that like if you could ever explore consciousness as a digital thing, as a digital interface, like I don't know, uploading like your mind to the internet or something. Which I would never do. Or
don't recommend that.
Do not recommend. But,
think twice about that one.
But it's such a interesting thing to play around, at least.
Yeah, I mean, as you're saying, there's no mathematical concept for that too.
Right.
Because it's like, again, biology having kind of interface really with all of the domains, as we're talking about, where we exist in classical mechanics because, if we run at a certain speed and we trip, like we're going to fall, like all these, mechanical principles apply to our movement, the movement of our limbs and our bodies, like how strong gravity is, for example, on a different planet would make it much harder for you to lift your arm, right? If you were on Jupiter, right, you'd turn into like a puddle because the compression and the density of your bones, right, can't put up with the force that's pulling you down, right? So we're kind of ingrained within classical mechanics being on the surface of a planet. But then also, as we talk about deeper layers on the cellular, right, we have this cellular awareness and cellular intelligence to some extent where we're interfacing with molecules, with the chemistry, and also allegedly as the science, advances with neuro stuff, they're talking about quantum fluctuations and how, again, electrical potentials can influence the brain. I mean, we have a technique now, transcranial magnetic stimulation, TMS.
Can you describe that?
Yeah. TMS is basically literally putting a giant magnet right here on your head, and they turn the magnet on. And again, when the magnet gets turned on, as we know, electromagnetism is one force, right? So the magnet then induces electrical current in the brain. So by placing that magnet and turning that magnet on, you can now activate specific parts of the brain, right? So now, again, knowing the physical principles involved in that. Yeah,
that really reinforces like how much your environment, affects, affects your being in a way, I mean, it's great that we have internet, Wi-Fi, and everything, but we also don't understand like if there are any consequences being constantly bombarded with these electrical fields and things like that, and people have their own reservations about 5G and their and I'm sure like there are like a bunch of research papers of people who are like studying this type of phenomena and have basically their own conclusions about it and stuff like that.
Right.
And
I mean, the thing is too is like these electrical potentials are affecting the brain. I mean, again, showing that a magnet, again, these magnets are very, very strong to some extent. So they are again able to allegedly, increase. They do increase electrical activity in the brain in specific areas, and it's being now utilized. But also, yeah, as you're saying, all these, especially since the technology has only been around for like 30, 40 years as far as cellular devices and things like that, we were making them stronger and stronger. They're able to now stream movies like, inevitably, like just they can constantly keep up a data stream of information because of the power of those signals and the amount of data that's just, again, flying through the air, and whether that affects the individual. I mean, they've shown brain scans, people talking on the phone with the phone close to their head, and there's changes in brain activity due to that. Whether those are good or bad things and like how it's going to affect the biology, again, the brain and cells maintaining their own internal equilibrium, but with another type of energy, present in terms of radio frequency, these frequencies we're operating, and we're still discovering what those do, and how to even utilize them as forms of technology, where they're going to interface with us. And interestingly enough too, it's like this is how we broadcast.
Yeah.
You know what I mean? In a way, again, because a radio receiver is just an oscillator. And if you oscillate at the same rate, you can share information between yourselves, right? And this for me is like, the crazy part of my mind goes into like telepathy. Because if my brain waves are syncopated, at a particular frequency, and someone else syncopates those brain waves with you, is information transfer possible?
But
Because
consciously, though, that's the differentiation, I guess, for at least for your case, is the other receiver able to consciously, interpret, tune
in,
and that is an interesting abstraction, because in a way, I mean, there are some people out there who talk about frequencies and quantum mechanics, you're in vibration with each other, or things like that. And at the same time, you also have a different camp where everything is brought down to a reductionist mindset. You can continue to break things down, and then when you break things down into its most simplest components, it's like the easy problem of consciousness. David Chalmers he was a guy who coined the hard problem of consciousness, and he talked about, well, we can break everything down to biological phenomena and explanations to how or why, but we can't actually explain how, in a way, I guess. How consciousness gives rise to
itself, really.
Exactly, itself and its experience, and and consciousness is not even included in the standard model. It's not like there's a particle that emits consciousness or anything like that. There's not even a particle that we can see that emits gravity. And this is why we go into this is why there are theories about string theory and multi-dimensional universes out there,
where this energy is embedded.
It's a little bit outside of my expertise, so I really can't explain too much, explain too well to your audience and to you, but it is a very, very interesting and almost compelling discovery, because at least when you take a step back from the daily life and the grind and things, you are reminded of there's a moon out there's a night sky, there's a day and night cycle, and there's just something infinitely larger than us,
and there's an inherent rhythm to all of that too. I mean, and that rhythm is embodied in us. There's studies of people going into caves, and they really do find that the circadian rhythm, or is kind of our ability to stay up 16 hours, sleep 8, of the 24, is embedded in our biology, and the way that our body operates is kind of taking in account those rhythms. But as we were saying before, in that ability to tune in, a lot of times, because in the modern world our consciousness is very externalized. I have to meet X, Y, and Z deadlines, right? I have to meet this person here at this time. I have to accomplish these tasks, right? And we're always here, and here, and here. And we, again, kind of, because of this externalization of our minds continually, we kind of, lose track of these deeper levels of self and these deeper levels of, tuning into what inherently biology is, right? I mean, as you're talking
beautifully said, yes.
As you're talking about, gravity isn't really found anywhere, but gravity, again, being an inherent property of matter itself, matter. And in this way, maybe we can think about matter implies gravity, just like electricity implies magnetism, right? Them kind of being one force to some degree. We could say, but.
And, just to tie things back up, when it comes to because in order to have physics, you at least need to have a ground layer of, I guess, calculation, and that's what we have as math, with numbers and and things like that. And even before numbers, I feel like math is just inherent in the tapestry of of nature, in a way.
Right.
It's not like we invented math; it's just we discovered it.
Yeah, it's already there.
Yeah, exactly. And so, and one thing about that is, when you put certain things together and set them in motion, you have shapes. You have very, very specific conditions of shapes. That are only possible. That are only formed through those differentiations. And that's what makes a circle, and a triangle, and whatever.
Right. Like proportion.
Right. And now we scale that out into into, let's say, everything we know. I guess you can kind of call it sacred geometry in a way. There is order to all this randomness,
Right.
And you kind of see that with entropy. In a very, very high entropy state, your environment is constantly like pushing you back to equilibrium, and yet and there is something within the in that experience to where you can either flow along with that entropy and just be taken over by it, or you just create your own entropic reaction against it, and stars form.
Yeah. In that case too, even just thinking about entropy, for those of you who are at home, you're like, what? Right? Entropy being just this force of diffusion that everything naturally in the universe wants to equalize, right? The cup of coffee eventually meets the temperature of the room. The body, is hotter than its environment. We're constantly giving off heat, right? So we're losing energy in terms of physics, right? But then then we eat again, right? And now all of a sudden we keep this, we bring in more matter, we break that down with acid inside our body.
Yeah.
And then again, incur function, continue to utilize the calcium and potassium and things in food, right? And then, build our structure out, facilitate all of this. But yeah, it's, again, these inherent properties of matter, which become really, really interesting, and how we operate and how the mind operates. And I think if we're going to go into sacred geometry, I think we might have to save that for another episode.
No, that's completely fine. I only brought that up because I just wanted to emphasize that if it's true that, that math and physics and chemistry and all of these things, they follow very, very specific conditions that allow life to exist, but they also have their own set of rules in a way. Consciously, we don't know what they are. We don't know we know 3.14 is pi, but it's not like you're born into this world and 3.14 or any other things.
Well, it's easy to do because again, these principles or these proportions inherently exist, but our system of number being based off 10 is something that we created, I believe. Proportions exist, exactly 3.14, the ratio of the inside of a circle to the outside of the circle, right? So it's a relationship. And in terms of, Einstein, as we were talking about, relativity kind of drives all of these phenomenons. How do these things relate to one another? Even when we talk about the mind, we have different layers. There's 6 layers of the cortex that all act and behave differently and share information in different ways.
And yet when a child is born, for instance, that golden ratio of 1.618 or whatever, it's what takes form of its physical physical form in a way, how the eyes are formed and it's and everything else, and it's like that part is just flowing inside of us,
Right. Yeah. Again, the physics, us being ingrained and embodied in physics, taking advantage of those principles, our body is utilizing those things. Again, as we talked about, even spin, the golden ratio leading into, the Fibonacci sequence and all of these things, and how that circle, but again, all these principles physically that we exist within, definitely sets a really interesting groundwork for the mind, the body, and the psychology to exist, so I want to thank you for coming on for today. This is a really great episode. I think we might have to do this again. I think we're going to have definitely talk a little bit deeper about the nature of reality, all these cool sorts of things. So thank you for watching in the Conscious Endeavor. Tune in again, throw something in the comments, tell us what you think about some of these things that Tae's talking about. Do some Googling and dive into it, dig it out, and we'll see you guys next time.
Thank you very much. Thank you for having me on.